All right, welcome back everyone to this month's Tech Talk. As you can see, this month we're going to be hearing from Alluxio on enabling fast big data analytics on Ceph. So Adit, would you like to take it away?
Sure, sounds good. Thanks, Patrick. Thanks everyone for joining. As we go through the presentation today, feel free to stop me at any time if you have questions or you would like to talk about something. Today, like Patrick said, I'm going to talk about how Alluxio can be used to speed up data analytics on top of a Ceph storage cluster. Okay, before we start, a little bit about myself. I'm a software engineer at Alluxio, the company behind the open source project. I graduated from CMU in 2013, where I worked on different distributed and storage system problems. And before that, I was an undergrad at the Indian Institute of Technology in Delhi. Feel free to get in touch with me after the talk if you're interested. My email is right there on the screen. It's adit@alluxio.com. So I'll start with a brief introduction of what Alluxio is and the ecosystem it's typically used in. As Alluxio, the open source project is actually one of the fastest growing open source projects in the big data space. The graph that we're looking at, it's showing us the number of contributors for different projects in the early stages of the project itself. So the x-axis is the number of months, and we can see that Alluxio has a vibrant and a fast-growing community, which is spread across different organizations, both in academia and in the industry. So the essence of what Alluxio does is connect any application to any storage at memory speed at any scale. To give you a little more context on where we're coming from, we started with a world in which we had one compute framework, which was Hadoop MapReduce, and there was one one storage system used typically with MapReduce, which was the Hadoop distributed file system. Then we saw a proliferation of different storage systems of every type of data and workload. We now have a world of possibilities, both on the compute side with compute frameworks like Sparc, with Flink, with Storm, which cater to a different kind of application. At the same time, we have storage which is spread across different storage systems like the S3 object storage. We have Ceph, and we also have things like ECS, which provides the storage backend. The problem that we faced in such a scenario was that the end application developer had the job of connecting their compute to this variety of storage systems, which was not an easy task. Now, what you can do with Alluxio is that you can configure your compute framework to work with Alluxio, and Alluxio itself handles all of the communication with different kinds of storage systems. So as an application developer, you only worry about connecting with Alluxio, and Alluxio can connect with different storage systems underneath. So Alluxio provides different kinds of interfaces. The recommended interface is the native file system like API that we have, which would give you access to any of these systems underneath. And to connect to the systems underneath, if you're connecting to the Hadoop distributed file system, you use the ATFS interface. In our case, when we connect to Ceph, we use the Swift interface to connect to Ceph. Okay, to summarize why you would use Alluxio is Alluxio has a scale-out architecture which virtualizes different storage systems underneath in one unified namespace. Alluxio works with any compute framework and storage system of your choice, and Alluxio delivers memory speed performance because it's co-located with the compute. I'll talk about this a little more about what I mean with Alluxio is co-located with the compute in later slides. Uh, the separation of storage and compute resources and the focus. I'll also focus on what the performance benefits Alluxio brings in such a scenario. Uh, Alluxio, like I said, it brings three main benefits. The first is to unify different storage systems. Second is high performance by running jobs at memory speed, as Alluxio is co-located with the compute. And you also save money by only by the compute and storage you need with the flexibility that Alluxio provides uh, with the separation of compute and storage. So here's the use case that we're going to focus on in today's presentation, which is to uh, accelerate I/O from remote storage with the use of Alluxio. Now, there are several benefits of separating compute and storage resources. You can use cost-efficient object stores. You can scale the resources independently on as needed basis, and you could also use big data frameworks without sharing any resources with the underlying storage. Now, however, a disadvantage of the separation between compute and storage is that whenever the compute framework has to access data, it takes longer because the storage is farther away and the network latency and throughput is low. Latency is high and the throughput is low. And this is exactly where Alluxio comes into the picture as the compute side data management layer. So if you look at the use case without Alluxio, in the example that I'm going to present today, I'm using Sparc as the compute framework, and I'll use Ceph as the storage framework. The box in the end could be replaced with Ceph. Now, whenever you're accessing data from the storage in the compute framework, you observe high latency and you're bounded by the network throughput which is available from storage system. However, if the same data was present on resources which are co-located with the compute framework, in this case, the same resources which are running the Sparc framework, you would observe low latency and high memory throughput. So in the case where you're using Alluxio, you would use Alluxio to manage all of the memory resources on the resources which are running Sparc. So in this case, we will configure Alluxio to manage memory only, but I would like to mention that Alluxio is not limited to managing memory, but it can also manage different tiers of storage like SSDs or HDDs on the resources which are running the compute framework. And while it is managing the resources, managing SSDs and HDDs, it seamlessly migrates this data into memory so that you can still access the data at memory speed in most cases. Like I said, keeping data in Alluxio accelerates the data access by the compute framework as it is close to the compute. Here's an example use case. People at Baidu were using Alluxio to accelerate storage, data access from a Baidu file system cluster. Alluxio was managing over 2 petabytes of data, both in memory and hard disk drives, and the size of the deployment was over 200 nodes. In this particular use case, Alluxio was able to bring performance benefits of over 30x by the benefits that I've already outlined previously. Okay, now that I've described the abstract problem, let's dive into the specific solution on how you would use Alluxio to accelerate analytics on top of Ceph. I will run through some basic instructions on how you would connect Alluxio with Ceph, and also how you would use Sparc to issue ad hoc queries. For demonstration purposes today, Alluxio connects to Ceph using the Swift API. So Ceph has been configured with Rados gateway, and all requests to Ceph storage pass through the Rados gateway. I'll show you experiments, results, and a demo video of running Sparc on top of Ceph. In the configuration that I have, I'm running everything on EC2. I'm using 4 types of machines, which I named the first type of machine is called a compute master, which is running the Sparc, which is running Sparc and Alluxio master processes. The second type of machine that I have are the compute workers, which is running Sparc and Alluxio workers, and I use 3 of these workers. The third type of node is a storage manager, which is running the Ceph Rados gateway daemon and also the monitor process. And then lastly, the actual data lies on nodes named as storage devices, which is essentially the Ceph OSDs. I'll use R3.extra-large instant type, and all of the machines have been launched in the same availability zone. Also note that this is not a requirement that everything has to be in the same availability zone. The benefits that Alluxio brings will only be amplified in the case in which the storage cluster is in a different availability zone, as we observe higher latency and lower bandwidth to the storage cluster. The versions that I've used Ceph Hammer, Alluxio, the recently released Alluxio open source version 1.4. I've used a custom JOS library in case anyone is interested in reproducing the numbers. JOS is essentially the client library that Alluxio uses to communicate with a storage backend which supports the Swift API. We found some limitations, and we have made some corrections to the JOS library. In case anyone is interested in knowing what those changes are, please feel free to email me, and I'll be happy to provide you with the custom library. The version of Sparc that we used is 1.6.1. I'll show you a quick 5-minute video of some of the things that I described. So before I start the video, Sparc, Alluxio, and Ceph have been pre-deployed on the configuration that I showed you. Ceph has been pre-populated with a 60 GB dataset. which is not present in Alluxio memory. So it's only in Ceph when I start the video. I'll show you a sample application of running queries in Spark using the Sparc shell. What we'll do is we'll run a simple Spark count job, which is counting the number of lines in a file, which is the 60 GB data set. I will run a second Spark count job, which will show you the performance of the caching effects in Spark itself, and also compare it with storing the data in Alluxio memory. I'll restart the shell, and I'll show you the performance of a third count. The implication of restarting the shell is that once you restart the shell, whatever data Spark had cached is lost. But this limitation is not present when you use Alluxio, as you'll see in the performance results that I share. So the third count that you do, you will see significantly higher performance with Alluxio in the picture. To end the demo, I'll show ad-hoc queries using Alluxio. But what I mean by that is that I'll store some. I'll issue a word count query in Alluxio. I'll store some intermediate data so that subsequent queries which use the same data set are much faster. Okay, I hope the font on the demo is large enough for everyone to see. So I'm going to perform all of the operations in the second shell that I have open. The first thing that I did is I already have Ceph configured as a storage system that Alluxio communicates with. Not in memory in the text that we see right now. It means that the data is not being managed in Alluxio, but Alluxio is aware of these files existing in Ceph storage. So there is a folder named data which has 20 files. Each file is 3 gigabytes, and which makes up our total sample data set of 60 gigabytes. It's only, like I said before, it's only in Ceph, and it has not been stored in Alluxio memory yet. The next thing I did was that I started a Sparc shell, which is an interactive process that we use to run compute jobs. Sparc has been configured with the correct libraries to talk to Alluxio. The first thing that we did was that because we want to observe the timing information of the compute job that I'm going to run, I set the log level to info, which will print some information. So yeah, I'm going to pause here. So the way Sparc communicates with Alluxio is using the Alluxio file system-like interface. Here, what we did was we created a file with the path to Alluxio. Ceph demo masters is the host name which has the Alluxio master process, and data is the directory that we are running our compute job on. So I just started the count operation, which is running, which is counting the number of lines on the 60 GB data set. So I have forwarded this. I have fast forwarded the actual running time of the compute job. This is a job which runs for 12 minutes. You can see that Spark is running with process local locality, which means that which also means that the data is not being fetched from Alluxio at the moment, from Alluxio memory at the moment. Both, for the sake of comparison, Alluxio has been configured with Alluxio, and when I do a direct access on Ceph, both have been configured with the 512 megabyte block size. What that means is that for the 60 GB dataset, there are 120 tasks created by Spark, and and we saw that the count job on Alluxio, the first count job that we did, it took 750 seconds, which is approximately 12 minutes. The next thing that we did was we reevaluated the file in Alluxio. This step is essentially fetching the block locations from Alluxio. So it is fetching the locations of the Alluxio worker processes which store the data. Now that the data has been fetched from a remote store Ceph storage cluster into Alluxio. You will see that now that we do the count job, perform this count job again, the count job finishes much faster. And also, which you can see that the tasks were run with node local locality, which means that the tasks have been launched on the nodes which store the data. In this case, the source of the data for Spark is Alluxio memory. So you saw that we got the same result, which for the number of lines that were counted, and the job only took 40 seconds because it was stored in the Alluxio memory. The next thing that I'm going to do is I'm going to exit the Spark shell, and I'm going to restart the shell and perform the same job again. Before I restart the shell, you can see that now when I do a listing on the data, it shows that it is in memory, which means that it is being managed by Alluxio. Now, a different Spark shell could also mean you have a different user accessing the same data, the same data set. So different shells could mean running the count job by the same user at a different time, or also by a different user at the same time. So we perform the same operations again. We reevaluated the data, the file, and we perform the count job. You will see that we still preserve the performance benefits that we saw in the previous case. Okay, so the next thing that I'm going to do is I'm going to perform some word count operations on top of the same data set and store the intermediate count results in Alluxio. What I mean by the intermediate count results is that once we calculate the count for each word, we store this information in Alluxio, which I call intermediate data, and then I will perform subsequent queries on the intermediate data, which is not accessing the entire 60 GB data set from from a remote Ceph storage cluster. Note that this job still takes a little bit time, even though it is stored in Alluxio memory, as this job is a compute bound job, and is not necessarily exercising the I/O benefits that Alluxio brings. So we saw that the job took about 400 seconds to complete, and as you can see on the screen over there, it took about 422 seconds to complete. The next thing that we do in the demo is we store the intermediate data in Alluxio in a file named 60 GB counts, which stores a key value pair. The key is the word and the value is the count of that word. And now we will issue subsequent queries on the 60G counts file. Note that I also exited the shell and restarted the Sparc shell so that to demonstrate that once the data is in Alluxio, it can be shared across different applications. So this is also relevant in the case in which typical big data workloads can also share data across different jobs. And the benefits that we see with Sparc caching are only applicable to the same job itself. So we saw that a subsequent query on top of the 60G count, which is counting the top 10 words, which is calculating the top 10 words in terms of the highest word count, took only 2 seconds to complete. A summary of what we went through. We looked at the performance of a Sparc count job on a 60 GB dataset. We saw that the first count, which was performed on Alluxio, it took about 750 seconds. We performed the same job without Alluxio, accessing Ceph using the HDFS file system API. HDFS, specifically the HDFS Swift connector to access data from Sparc. We observed that the job took approximately the same time. Now, when we do the same operation in the same Sparc shell for a second time, Alluxio took a little bit less time than it took to run Sparc on top of the data which is cached in Sparc. The difference in the second count that we have over there is that in the blue bar, data is stored in Alluxio, and in the red bar, the data is stored in Sparc. What we did next was we restarted the Sparc shell which is simulating another application, and we perform the count job again. In case of Alluxio, you can see that when the data was being accessed from Alluxio memory, it took approximately 20 times less time as it took to access the same data from a remote Ceph storage cluster. And this is the performance benefit that we see with when accessing data from Alluxio for repeated accesses. We also have a white paper on the use case that I just described. If you're interested in looking at how you would set up Alluxio on top of Ceph with Sparc, the white paper has detailed instructions on doing that. And the blog would give you a brief introduction on what the white paper is talking about. Thanks for attending the call, and I'm open to any questions that you may have.
All right. Does anyone have any questions for Adit? Feel free to speak them out or type them in the chat. All right. Sounds like no. All right. Well, thank you very much, Adit. Appreciate you coming to do the Tech Talk. This will be available on the YouTube channel probably within the next week or so, probably the next couple of days. The next Ceph Tech Talk will be on March the 23rd at the same time. Stay tuned for the details on that as we get a little bit closer. But thank you, everybody, for joining us, and we'll see you again in a month.